Good morning, esteemed experts. The title of the paper I will be presenting is Detection Facial Features Enhanced Multi-Branch Graph Network for Driver Drowsiness Detection. I will provide a detailed introduction to the research methodology of this paper from the following 4 aspects. Driver fatigue has been identified as one of the primary contributors to traffic accidents, highlighting the importance of real-time fatigue detection for enhancing road safety. Conventional fatigue detection approaches often assess fatigue based on facial features such as the eyes and mouth. Accurate fatigue detection remains a challenging task when facial features of the driver are partially missing. Missing features can be caused by lighting changes, occlusion, or head pose, which makes traditional facial-based fatigue detection more difficult. Traditional per-close-based fatigue detection methods assess driver drowsiness using the eye aspect ratio (EAR) for eye closure and the mouth aspect ratio (MAR) for mouth opening. However, the accuracy of traditional facial fatigue detection methods cannot be guaranteed in scenarios where facial regions are partially occluded. Our paper focuses on addressing the problem of driver fatigue detection under partial facial occlusion, with the goal of improving the model's robustness and detection accuracy in the presence of incomplete facial features. Figure 1 presents the MBGN architecture. The lib first extracts key facial landmarks, left eye, right eye, mouth, which are transformed into graph nodes and processed by separate feature extraction branches. In the branch graph network, GCN captures spatial relationships between nodes and learns to map features to facial fatigue states. During the third stage, an adaptive learning weight network, ALWNet, is utilized to dynamically assign importance weights to each facial region. The weighted features are obtained by multiplying the learned weights with their respective regional feature representations. Finally, the 3 weighted features are concatenated into a single feature vector. The concatenated feature passed through a multi-layer perceptron MLP for regression to obtain the probability-based detection result P, where P ranges from 0 to 1. Figure 2 illustrates the structure of the branch graph network module. The inputs of GCN are mainly node, feature matrix X, and node adjacency matrix A. In our study, the facial landmarks detected by DLIB are transformed into graph nodes, and the nodes are sorted based on their horizontal and vertical coordinates. Subsequently, the position coordinates of the regional landmarks are used to construct the node feature matrix X. In our study, the Euclidean distance between each landmarks is calculated from their coordinates to construct the corresponding adjacency matrix A. By constructing the graph nodes, the main inputs to the MBGN model are 3 graphs. Each of these graphs is fed into a dedicated branch graph network to extract representative features. As illustrated in Figure 2, each branch graph network module is composed of 2 graph convolutional network GCN blocks. The detailed computation process is formulated by the equations shown on the right. The accuracy of landmarks detected by the DLIB algorithm is significantly reduced in occluded regions. The integration of these less accurate landmarks with other precise features can reduce the reliability of the final detection result and cause contradictions with other features, negatively impacting the model learning process. Therefore, based on the branch graph network, we introduce an ALWNet to dynamically learn the optimal weights for the features from each branch. This enhances unobstructed facial features and reduces the impact of occluded regions on overall features, improving detection accuracy. The proposed ALWNet adaptively detects the degree of alignment between the graph nodes and their corresponding regions in the image, assigning proportional weights omega to branch features within the overall feature representation. Firstly, eye contour features are initially extracted using a 3-3 convolution with the number of convolution channels C of 32, a striative 1, and a Aurelio activation function. 2. Further enhance feature learning. A spatial attention module, SAM, is incorporated, as shown in Fig. 3b. Considering variations in the sizes of cropped region images, spatial pyramid pooling SPP is employed to unify feature map dimensions as depicted in Fig. 3c. In SPP3, pooling layers with sizes of 1, 1, 2, 2, and 4, 4 are employed to compute the features, and a fixed-size feature vector C21 is outputted after the concat. ALWNet evaluates the degree of alignment between graph node shapes and their corresponding regions in the image to determine occlusion levels, reducing output weights for regions with low alignment. The dataset employed in this study comprises 3 publicly available datasets, namely YAWDDDD and DROSY, in addition to a synthesized dataset. To further enhance the model's occlusion resistance, we manually added facial occlusions such as sunglasses and masks by synthesizing 5,000 images selected randomly from the unoccluded images available in the dataset mentioned above, as shown in Fig. 4. To better show the performance of our method, we compared it with the traditional per-close-based baseline and other popular facial drowsiness detection methods. The baseline relies heavily on eye and mouth landmarks, making it prone to failure under occlusion 72% accuracy. Our method improves accuracy by over 20% across 3 public and 1 synthetic dataset. Figure 5 shows the MBGN model's classification results for both drowsy and normal states. The green boxes are glib tracking boxes, showing the predicted probabilities. As we can see, the MBGN model still detects drowsiness accurately even when facial features are partially occluded. To show how well the GCN module works in the MBGN model, we did ablation experiments using several common image classification models on the same dataset and compared their accuracy. The results show that using GCN to extract features directly from landmarks helps reduce noise from other parts of the image and boosts detection accuracy. To verify the effectiveness of the MBGN model in detecting driver fatigue under different occlusion scenarios, we synthesized 4 types of occluded data images: left eye, right eye, both eyes, and mouth for experimental evaluation. Table 3 shows that covering just one eye, left or right, doesn't affect detection accuracy much. But when both eyes are covered and their landmarks are missing, the accuracy drops. Since the mouth has more landmarks and stronger signs of drowsiness, covering the mouth causes a bigger drop. Still, even when both eyes or the mouth are blocked, the model keeps accuracy above 96%, which is still acceptable. Proposed a multi-branch graph network for facial drowsiness detection with improved accuracy. The introduced adaptive weight learning network can dynamically adjust the contribution of facial regions by learning their true importance, thereby reducing the impact of occluded areas. Current experiments rely on manually augmented data, but the dataset is still limited and lacks scene diversity. Varying lighting conditions affect facial feature clarity and extraction accuracy. Future work should expand datasets with more diverse lighting and individual characteristics to improve model generalization in complex scenarios. Existing facial fatigue detection algorithms overlook fatigue-related features in the temporal dimension. As the model does not consider temporal dependencies, it's difficult to track node position changes across frames. This concludes my presentation. Thank you for listening. I welcome any feedback or suggestions from the esteemed experts.